Hello and welcome to 16th lecture in our comprehensive course on AI, ML and DS. We are currently doing chapter 19, basic statistics. However, this was a long chapter. In first part of the chapter, we did about various measures of central tendency and various measures of dispersion. In second part of the chapter, we did about various types of data distribution and we did a very detailed discussion and we stopped here why understanding data distribution is important in data science, right? Now, at the end of the chapter, I told you that here we want to start the third and the last portion, inferential statistics. The previous two portions, they deal with what we call descriptive statistics. But now we want to talk about inferential statistics. However, there is one thing. We want to first discuss this central limit theorem. This sits somewhere at the boundary of the descriptive and inferential statistics. That means understanding central limit theorem helps in both descriptive statistics also and inferential statistics also. And if you remember, much earlier when we discussed population and sample, at that time we discussed one this kind of case. That suppose you are asked to study the customer behavior of a large online retailer like maybe Amazon or Flipkart, and you want to, as a data scientist, you are given say a data of 2 million customers spread across maybe 100 countries, and in each country spread across various states and cities. Now what you have to do, you cannot study 2 million customers and build a predictive model using all. Even if you have the necessary computing power, it is not required to do it. The reason is that this central limit theorem guarantees that, and when certain conditions are satisfied, and at that time while discussing this, I told that what are certain conditions that we will do later on. But when certain conditions are satisfied, then if you take a proper representative sample like this, so you should not take a lopsided or skewed sample this way. Maybe this is a whole sample of only one country, say India, but that will not explain the behavior of customers in US or UK or maybe Australia or other Japan or other countries, right? While Amazon has its operations in several countries. Similarly, this might be the data set of Walmart. Now, Walmart has its operation in around greater than 140 countries, as far as I know. So, you have to take a representative sample. That is, take around say 100 to 200 observations from one part, another 100, 200 from one part, another 100, 200, 200 from one part, and so on, covering all the entire population. And you have to take certain other case. So, suppose you have made this sample of 5,000 observations, which is truly representative of your data, and the observations are independent and they satisfy certain conditions. Then in that case, I told you that when you estimate the sample mean, that is mu, that gives a fairly decent idea about population mean, that is x bar. Not only mean, but all measures of central tendency and even measures of variance, that is dispersion, like variance and standard deviation. Whatever you find for sample, they give fairly decent idea about the variance standard deviation of the population. Okay, so as a result, you can say that there is no need to study entire population of 2 million data sets. It is sufficient to study this sample, and all the statistical results which are obtained from this sample, they are also applicable to the population, provided certain conditions are satisfied. This is what is guaranteed by this central limit theorem. So now we want to do in this detail about what is that central limit theorem and what are those conditions, right? So the central limit theorem is one of the most fundamental and powerful concepts in statistics. It describes the behavior of the distribution of sample mean or sample sum or other statistical parameter. But sample mean is how it's a statement. When you write the statement of the theorem, then at that time, statement is written in terms of sample mean. So it describes the behavior of distribution of sample mean when we take random samples from population. So here is the essence of the theorem. Now definition word is written. Definition is not very correct word. Instead, it should be statement. The statement of central limit theorem. If we draw many random samples of size small n, here in that case, the small n was 5,000. Okay. So if we draw many random samples of size say 5,000 from any population of size large n. So here large n was the 2 million customers data of maybe more than 100 countries. Okay. And if that sample has finite mean and the variance equals sigma square, then the distribution of sample mean will tend to follow normal distribution as n becomes large and large. regardless of the original population's distribution. Now, what is the meaning? Please try to understand. Okay, suppose this is my population, and the central limit theorem says that your original population may be following any kind of distribution. So that means it may be normal. Fine. If it is normal, well and good. Population distribution is normal, then well and good. But if it is not normal, then it might be some totally different distribution. For example, it might be, say, uniform distribution. We have done data distributions, so we know that this kind of distribution between two variables, two constants A and B, that is called uniform distribution, right? So this is A and this is B. Or it may be exponential distribution. So in that case, your population might be following maybe this kind of distribution, this, okay, because we have plotted all this distribution earlier, so we know, and this diagram also we have, so we know that this kind of diagram, right? So this is normal distribution, then exponential is somewhere this, so this is exponential distribution, and uniform, this is uniform distribution. So my original population, that is these data points which are shown by black color, and there are millions and millions of data points, may be spread like that, so that I plot a KDE plot or showing the distribution of the data points or their probability distribution, then that comes out to be maybe normal, maybe uniform, maybe exponential, or any other type of distribution. But the central limit theorem says that that original population's distribution, that is this big bubble, black colored, that does not matter. What matters is that what kind of sample you are taking. So suppose I have taken one blue sample, now I am taking another this kind of red sample, and there are thousands and thousands of data points in each sample, okay. Similarly, suppose I am taking now, say, one this brown sample, maybe another I take this kind of sample, similarly another maybe this kind of yellow sample, similarly I take green sample, and you can see that I am taking my sample such that various samples are independent of each other. Another light green and fluorescent green sample, okay, then another maybe orange sample, and so on. So now read the statement. So some things at least will become clear, that the statement of central limit theorem says that if we draw many random samples of size small m from a population of size n, each sample should have finite mean and variance, and similarly population should also have some finite mean x bar and variance, say s square or sigma square, whatever symbol you are using for population, then the distribution of sample means will tend to follow normal distribution. So remember, I am not saying that the data point inside this each sample, they are normally distributed. That is not possible, because if my entire population is not normally distributed, say my population is like this or maybe like this, then if I take different samples, then there also there is no question that the data point or the probability distribution, both data distribution or probability distribution, would be normal. But if I find a mu of this, okay, let me select some other type of line, okay, so if I find the mu of this, then mu from this sample, mu from this sample, mu means the mean of each respective sample, then mu from this sample, okay, all mu's also will be different, because the samples are radically different, so their mean values will not be same, correct? But if I draw different samples and find mean of each, so in that case, this from green, suppose, is the, okay, I will show the mean of each by the same color as the sample size, and for that I am pausing the recording because I don't want to waste time for that kind of thing, so just let me write means, okay. Okay, so now you can see blue sample, its mean is mu4, the red sample, its mean is red colored mu3, the green sample, its mean is green colored mu1, orange sample, its mean is mu5, this fluorescent green sample, its mean is fluorescent green mu6, this yellow sample, its mean is mu7, and so on. So what I am doing is I am taking several large number of different samples from my population, okay, and I am finding the means of all population, all samples. Now clearly this means will not be same, so mu1 is not equal to mu2, is not equal to mu3, is not equal to mu4, correct? But this theorem says that, okay, if I plot a graph of, and that graph I am plotting in, say, blue color, of mean of various different samples, that is on this xy axis. I am putting all these mean points, mu1, mu2, mu3. So one mean is suppose this, one mean is suppose here, next mean is suppose here, next mean is suppose here, next is suppose here, still next is suppose here, still next is suppose here, still next is suppose here, and so on, right? So if you get mean in this manner, like that, okay, and draw a line passing through all these means of large number of samples. Now these are only 5, 6 are shown, but ideally you can draw as many samples as you want. These are the 2 million customers data, from which how many samples of 5,000 can be drawn. So naturally you can draw maybe around 20,000 or so samples. So find the mean of each sample and then plot them. Then the central limit theorem says that your original population had a distribution like this, or like this, or like this. So it may or may not have normal distribution, but there is a guarantee that for all this, whether original population is already normal, or whether the original population is uniform, or whether the original population is exponential, or whatever is the original population, there is a guarantee that the means of various samples which are drawn randomly from that population, they will always follow a normal distribution. Okay, now this theorem is, now if you read the sentence, then it becomes clear. If we draw many random samples of size n, so if I put this as minimal, then I think I can keep it. So just for the sake of more relatability, so if we draw many random samples of size small n from any population of size big N, here big N is say 2 million customers data and small n is that 5,000 each sample size, and if that big N has some finite mean and variance, then in that case, that is the population should have finite mean and variance, then the distribution of sample means, so find mean of one sample, second sample, third sample, so on. Suppose 20,000 samples are taken, then find the means of all samples. Then this blue colored here, the distribution of sample means, where I am at present moving my cursor around it, that is always normal as n becomes large. So as long as there is one condition satisfied, that the number of population which you draw from, number of samples which you draw from your population, that should be sufficiently large, then this sample mean distribution, sample means are always normally distributed regardless of original population's distribution. Now that is very important, that original population may or may not be may or may not show normal distribution, but the means taken from the samples will be always normally distributed. This is the mathematical expression of it. Let x1, x2 up to xn be independent and identically distributed random variables from a population with mean mu and standard deviation sigma. So mu, this mu, which I have written that it should be finite, okay, and this variance is sigma square. So this sigma is the standard deviation. So that two are the quantities which are related with entire population. Now that means symbols keep on changing. Some books write x bar for this. That is okay. But then let this be mean and standard deviation, and this x1 to xn. So what will be this n? This n would be at that time this size of my sample. Okay, so this is my size of my sample. Okay, then what is the sample mean? Then sample mean can be found. I told you that first find mean of each sample. So sample mean, its definition we already know, that sum of all observations divided by number of observations. So sigma I equals to 1 to n xi divided by number of observations n. So here also this is sample mean mu. This is population mean, and so here symbols are interchanged. We used to take these for simple mean and used to take these for standard deviation, but that is okay. So this was, for our case, we used to take these for sample mean and this we used to take for population mean, but now they have interchanged the order, so that's okay, no problem. So that means this is now sample mean x bar, and that is 1 by n sigma I equals 1 to n xi. So that is the sum of all observations divided by number of observations in each sample, right? But what the statement says, that if there are sufficient, as n becomes large, now mathematically this is written this way, as n tends to infinity, then the distribution of x approaches. So at that time this x bar, its distribution means if I plot various samples x bars on a graph, just like this blue x and y axis show the distribution of sample means, right? So the distribution of sample mean approaches a normal distribution. This is the symbol for a normal distribution with mu and sigma square by n as the two characteristics. So that means this mu is the mean and sigma square by n, that is the variance for that this distribution. Okay, so what is the mean of this distribution? That is the same as mean of original population. Okay, but what is the standard deviation of this normal distribution of means? Then the normal standard deviation of the normal distribution of means is standard deviation square or variance of this normal distribution of mean, then that is variance of this population divided by the number of observations in each sample. But this symbol is just showing that this distribution characterized by this much mean and this much variance approaches a normal shape as small n approaches infinity. So that means as the number of observation becomes larger and larger, this distribution will become more and more resembling to a normal distribution or a bell curve, right? Okay. So hopefully you are clear. The important point to note is that this is distribution of means of sample. This is not distribution of data points inside each sample. Okay, that is point number one. Point number two is that the central limit theorem says that the distribution of means of each sample. So each of these sample has mean somewhere, mean value somewhere inside them. Okay, which I have shown outside like this, but these are means. So then those means, if I find, they are always distributed like bell curve, and the mean of that distribution is the same as the mean of population. Okay, so mean of that distribution is mu, but mu was the mean of population. Okay, so that is correct. And the variance of this normal distribution of means is the variance of population divided by the number of observations in the sample. Okay, this is what is called central limit theorem. Now there are proofs also to do that, but rather than proving it, we will show it by demonstration, code demonstration. That will become easier. So we will try to initially take a small sample of this, say just 5 observations or 10 observations. Then you will then find mean of each sample, and you will see that that mean will not be following much of normal distribution. Then we will increase the number of samples. At present here there are 7 samples. We'll make, instead of 10, say 100 samples. Then you'll see that slightly normality starts appearing in the distribution of means of all those 100 samples. Then we will take 1000 samples and find mean of them and plot all of them on these axes. Then at that time you will see that a perfect bell curve will emerge. So proof is not important, but this theorem is extremely important. Why? Because this theorem gives predictability of sample means, that regardless of how the population is distributed, population may be skewed, population may be uniform, population may be bimodal, population may be of any type. Okay, if the sample size is large enough, sufficiently large sample size is taken, and second thing is the number of samples is large enough. Now large enough means how much, that also I will tell you. But if the sample size is large enough and number of samples which you take, independent samples which you take from your population, that are large enough, then in that case the distribution of sample means does not depend upon the original data distribution of the population. Okay, this theorem is the foundation for statistical inference, because you will see that, that's why I say that it sits at the boundary of descriptive statistics, because this is descriptive statistics. We are plotting the distribution, but we are slowly going towards this thing, inferential statistics, hypothesis testing, confidence interval, linear regression and all that. So at that time, this theorem is the reason why we can do all these things. Otherwise, if central limit theorem would be wrong or it would not be obeyed, then our current hypothesis testing methods or in confidence interval methods and linear regression methods would give totally baseless and wrong, false conclusions about our population. But because central limit theorem is right, that is why we can use this statistical technique. Now let us try to do graphical demonstration. Okay, so now I am minimizing this part and maximizing this. Now graphical demonstration means, I told you that we will take original population distribution, which is deliberately we are taking something which is not normal. Okay, so population is equal to np.random.exponential. In previous lecture we had done that np is a very versatile library. It can generate random, it can generate binomial, it can generate Poisson, it can generate exponential, it can generate log series, or even more different distributions, right? So here I am deliberately taking exponential distribution, which is not normal, right? So population is np.random.exponential. Scale is equal to 2. Scale stands for standard deviation, and size is equal to a very large population, around 1, 2, 3, and 4 and 5. So that means 1 lakh or 0.1 million. That many data points we will take in the population, because population is always large number of observations, right? Okay. Then from which we will select the sample sizes. So first we will select deliberately a sample which is not satisfying the condition of central limit theorem. A sample in which there are only 5 observations. But the central limit theorem says that if sample is sufficiently large and if we draw sufficient number of samples. So here I am taking such small samples that in each sample there will be only 5 data points. Then next time I am taking such samples so that in each sample there are 30 data points. Then next time I am taking such a sample so that in each sample there are 100 data points. Okay, And how many such samples I will take? Because central limit theorem says that number of samples should be sufficiently large. So I'm taking 1,000 such samples. Okay. Because even if I take 1,000 and suppose in each sample there are 100 data points, that would completely exhaust my this whole population. And in this case, even my population will not be fully exhausted. And then we will decide. This is now plotting. So plt.figure standard steps, plt.figure, then plt.subplot if you want to plot multiple plots on one, then plt.type of plot, hist plot or box plot or whatever, then plt.title, plt.xlabel, plt.ylabel, plt.grid if you want to show grid, and so on. So same steps which we have been doing so many times in our course, same steps are there. Okay. And first we draw histogram of population, entire population of 1 lakh data points, right? Or 0.1 million data points in 50 beans. So we divide it into 50 groups or partitions. Alpha, that is just a transparency setting, and color equals. And we plot give the title original population. So this much I will take first in a one cell, and let us plot it. So you can see this is my original population. So deliberately I have taken an original population which is not like this, normal, but I have taken an original population which is like this, exponential, right? Now let us take sample of these sizes 5, 3 and 100 from this population. Okay, so for I and sample size in enumerate, sample sizes is this list, right? So it will traverse through this list. That means first time it will take 5 as the sample size, next time it will take 30 as the sample size, and next time it will take 100 as the sample size. Start is equal to 2, sample means is equal to np.mean. Now this is also just a formula for mean of that, np.random.choice population sample size. Now what is the meaning? When I have taken sample size is equal to 5, so at that time this np.random.choice would be this entire population from which a sample of size 5 would be taken. Then next time when I take sample is equal to 30, then again np.random.choice from this entire population randomly 30 data points would be taken. And finally when I take 100 sample size, then from this entire population at random 100 data points would be taken. Okay. And how many such how long I have to execute my this least comprehension? Then for this underscore in the range num samples. So that means range num samples is equal to here 1,000. So I have to take 1,000 such samples like this. Okay. So then find the mean of it, take the subplot and plot histogram for the sample means. Okay. Then take 50 beans here also we have taken 50 beans for the entire population. Now for each sample mean, so that means how many histograms will be plotted? 3 histograms, one for this sample size, one for this sample size, and one for this sample size, right? Okay. And for each histogram, how many times the for loop would be for each sample size, how many times the for loop would be executed? 1,000 times, because you want to take total 1,000 samples of 5 size, then you want to take total 1,000 samples of 30 size, and then you want to take total 1,000 samples of 100 size, right? And each time you plot the mean, find the mean of each sample, and then plot it on histogram. And let us show that plot. Now that clearly shows that when the number of observations in each sample was less, only 5, then the sample means do not follow normal distribution, as the central limit theorem puts the condition. That what is the condition? That here, if we draw many random sample of size n from population of size n, then the distribution of sample men will tend to follow normal distribution. But when n becomes large, so sample size becomes large, right? So then next time we are taking n is equal to 30. So compared to upper one, this graph is at least closer to not being normal, right? And then next time we take sample size is equal to 100, this, and take 1,000 samples and plot the mean of each sample, histogram of each sample, and then you get this kind of data distribution, which is fairly very close to normal, right? Now I can even do it further. I mean, if I want to do, say I can add 1 or 2 zeros here, though it will take a lot of time if you try to do that on your laptop. But I think I have a little bit powerful system, so mostly there should not be issue. Okay, so now I have increased my sample size, third time sample size, instead of 100, I have made it directly 10,000. Okay, and let us plot it. It takes okay, no, it is here. Okay. Now for 10,000, you can see that it is even closer to the normal distribution. Okay, so as compared to 5 and 30, this is much more normal distribution, right? So you can use SNS also to plot the KDE, kernel density estimation, along with the histograms, but it is sufficient. So as sample size increases, the distribution of sample means become approximately normal, even though the original population is not normal. Okay, So original population is not normal, but the means of different samples, they are normally distributed. Okay. Now, where is the key? What are some key assumptions of this? Because I went on saying that thing, that when certain conditions are satisfied, then so now the question is, what are those certain conditions? Because we want to use central limit theorem, it looks to be very useful theorem, but we have to be aware about its limitations, or under which condition it is usable and under which condition it is not usable. So that we will take in next lecture. Thank you.